Wind is defined as gas in motion. Although wind is usually moving air on Earth, wind in outer space can be highly charged gases called plasma moving away from a star or hydrogen escaping from the atmosphere of a planet. On Earth, we classify winds by two main characteristics: their strength, that is, how fast and with how much force they blow, and their direction, which we name by finding the direction from which the wind originates. For example, north winds blow from north to south. Anemometers determine wind speed, which is measured in a unit equal to 1.15 miles per hour, called a knot. Sustained winds are graded on the Beaufort number scale. Breezes of less than 27 knots fall between 1 and 6, while hurricane gales over 64 knots qualify as a 12. 13 through 17 on the extended scale rank extreme storms of 65 knots to over 120 knots. Wind is produced when the Earth's surface is not heated evenly by the sun. Air over warm Earth rises and causes an updraft. When this happens, cooler air rushes in to fill the space left behind. The stronger the updraft, the stronger the wind. Since air over land heats up and cools down more rapidly than air over water, there is almost always wind near lakes and oceans. Winds have a large impact on the Earth. Winds carry atmospheric moisture from place to place, causing rain. The strong winds of hurricanes and tornadoes cause tremendous amounts of damage, and winds erode landforms as well as sculpt the faces of mountains. Humans have learned to harness wind power for many uses. Wind drives large turbines that make electricity.
But current produced in this fashion has an interesting feature. It is alternating. We can better understand this characteristic if we study the coil's rotation. Note that the particles flowing through the circuit represent electrons, but keep in mind conventional current flow is opposite in direction. By looking at this simple generator, we can see most current is produced when the conductor passes through magnetic lines of flux at the fastest rate. That is, the greatest current occurs when the conductor moves at right angles to the magnetic field. Then, as the conductor continues its rotation at a constant speed, it cuts through fewer and fewer lines of flux, and less current is induced. Eventually, the conductor moves parallel to the field. At this point, no current flows because the conductor doesn't cut through any lines of flux. This occurs twice in each revolution. Notice, as the coil rotates, one of its sides cuts downward through the magnetic field, causing current to be induced in one direction, while the other side is moving upward, inducing current in the opposite direction. After the coil passes through the position of no current flow, the previous downward side moves up, and the previous upward side moves down, thus reversing the current flow in the external circuit. This, then, is alternating current, a flow of current in a circuit that reverses direction periodically and is continually varying in magnitude. So how can we construct a source of direct current? Obviously, we must find a way to maintain current flow in one direction in the external circuit. To do this, we need change only the slip rings, which collect alternating current, to a commutator which will rectify, that is, change, AC to DC. The commutator is a collar divided into segments, insulated one from the other. We attach one end of the coil to one of the segments and the other end to another segment. Now, as the coil rotates through the first half cycle, the induced current of one direction is collected from the commutator segment. It flows through the external circuit, then back to another commutator segment and into the coil, completing the circuit. The brush that connects the commutator to the external circuit breaks the contact with the first commutator segment and makes contact with the second. As we've seen, the induced current in the rotating coil is opposite in direction from that of the previous half cycle. But the commutator switches the coil connections to the opposite side of the external circuit. In the external circuit, the current generated from the second half cycle is in the same direction as that generated from the first half cycle. The commutator has rectified the current, converting it from an alternating current to one that flows only in one direction, direct current. But
Wind blows, that turns swag.
And now we're going to look down on the blades from the top. Here we have the wind, and the blade is at 0 degrees to the wind. And at this angle, there's absolutely no torque on the blade or rotation of the blade, because the wind is actually pushing the blade that way. It's not going to rotate. Here the blade is at 90 degrees to the wind, and the wind is just going to go right by it. So there's going to be no torque again or rotation of the blade. Here the blade is at 45 degrees to the wind. Okay, that's going to provide some force that will rotate the blade, and you'll see that the force of the wind pushes this way, and the blade will have a tendency to rotate this way, away from that force. Okay. However, at this angle, when the blade rotates, there's going to be resistance. That's as it spins, and it's going to be a large resistance. I mean, if the blade was up and down like this, and it did spin, that would be the largest resistance, but it wouldn't spin because the wind would just go right by it. But even at 45 degrees, there's a lot of resistance, so you can reduce that angle. And here we have a 25-degree angle, and as it rotates, there's less wind resistance. However, you have to be careful how low the angle goes, and
How many?
Water pumper. The farm windmill is a bad design if you want it to generate all the electricity needed for your house. This is because it concentrates on capturing low wind speed energy. The farm windmill was designed to be most efficient in low wind speeds from 3 to 10 miles per hour. These wind speeds are the most common. The trouble is there is little energy in such low wind speeds. The result is the farm windmill would pump a small amount of water at a time, but do so on a more consistent daily basis. When the wind speed increases over 10 miles per hour, the efficiency of the farm windmills with their 10 or more drag blade rotors goes down. Its rotor will turn faster, but the percentage of wind energy capture decreases. By contrast, a modern wind turbine rotor using 2 aerodynamic lifting blades has its efficiency go up as the wind speed increases. It rotates faster, and its torque also goes up. It takes a lot of torque to turn the gears in a gearbox that makes an electrical generator spin fast. To generate a lot of electricity, you need to capture the greater energy in the higher wind speeds. Each time wind speed is doubled, you get 8 times as much power out of your wind turbine. the power of the wind is cubed. For example, a rotor with an 8-foot diameter with 2 aerodynamic lifting blades in a 5-mile-per-hour wind would generate 10 watts. The same rotor in a 20-mile-per-hour wind would generate 610 watts. Thus, it generates 60 times more electricity than it would in a 5-mile-per-hour wind. By contrast, a farm windmill with the same diameter rotor with 10 or more drag blades could only generate 8 times more power in a 20-mile-per-hour wind. Thus, a 2-bladed rotor is far superior to a 10-bladed rotor in generating the electricity for your home.
As number of blades on wind turbine increases, aerodynamic efficiency increases, but in a diminishing manner. When we move from 2 blades to 3 blades design, there is an increase in efficiency of 3%. But when we move from 3 blades to 4 blades design, efficiency gain is marginal.
On your dick.
Alright, we got you.
On your dick.
Alright, we got you. Fucking fuck! You can't just leave it there. Because it's gonna.
How many gigawatts we getting? How many gigawatts we getting?
Too many.
Really?
1.8.
1.8?
What would you say if I told you a wind turbine this size could produce the same amount of electricity as one this size? With the Root wind turbine's new design, this could be possible. What we did was add a windmill with rotating flaps and a heavy flywheel. When a breeze hits the windmill, it turns the flywheel that's connected to the electrical generator. With the greater surface area and the added inertia of the heavy flywheel, you'll be able to connect it to a larger generator and produce more electricity. A 3-blade wind turbine and the Root wind turbine both rotate in the same diameter, but here's the difference in surface area: the 3-blade model and the Root wind turbine. It's like a sailboat. If you wanted to move faster, you just put up all the sails to collect more of the wind's energy. If you have a steady 12-mile-per-hour wind, a typical 8-foot wind turbine will produce 160 kilowatt-hours per month. The Root wind turbine has the same weight and surface area as a 22-foot wind turbine, which produces 1,213 kilowatt-hours per month. That's a 758% increase.
In this experiment, a simple horizontal axis turbine was fashioned using a VCR tape motor to which 15-centimeter spoon-shaped blades were mounted via a semi-rigid rotor hub. Design variables included the mass of blades, no weight added, or 5 grams added. Using a constant wind source, the rotation rate of the blades, RPM, and the voltage output, V, of the motor for each of 4 designs were measured. Spoons were used for blades and were mounted onto the plastic lid centered in the pie sectors. One blade was colored in blue so that turbine rotations could be more easily tracked. For weighted blades, 2 pennies, weight 5 grams, were hot glued to each spoon. Figure 2D. The turbine was then placed on a chair in an indoor non-ventilated room, creating a wind-free zone. For wind production, a hose was attached to the back end of a portable vacuum cleaner so that air would blow outward. The hose was set up so that the wind would blow at the blades from a direction perpendicular to the blade rotation axis. The hose was secured to a hole in a large wind frame so that it would provide a steady source of wind for the turbine. A voltmeter was attached to the VCR motor's output wires to measure the current generated by the rotating turbine. Each turbine design was tested 5 times, since the rotation rate was not able to be measured by visual inspection. The turbine rotation was videotaped for 30 seconds. Then, by slowing down the recording, the rotation rate was accurately measured using the time code of the video recording. For each trial, the voltage displayed on the voltmeter was recorded. The voltage was recorded as a range because the values fluctuated slightly as the turbine spun. The median value of the range was used to calculate the mean voltage of 5 trials for each design. These are the results. The model with 3 weighted blades exhibited increased mean voltage and rotation rate in comparison with the unweighted 3-blade model, indicating that the addition of weight to the blades improves output. This work showed that adding weight to the blades each independently improved the turbine's efficiency. The finding that increasing the weight of the end of blades improved the turbine's efficiency was consistent with the prediction, which was in turn based on the notion that heavier blades would exhibit greater torque. Thus, the torque will increase if the mass increases, provided that the acceleration is constant. However, there may be an upper boundary beyond which the increasing weight of the blades will not be helpful, because very heavy blades are unlikely to turn at all.
Now, if I rotate the one on the left anti-clockwise once, it's got 8 teeth. Each tooth engages with the tooth on this wheel, and this means that although this rotates only once, so I'll say it rotates once, this one will rotate actually twice. Now, normally when we're defining ratios, we put it down as, say, we can say the ratio here is 8:4. But of course, we can simplify that, and in fact, the ratio is 2:1. We would say that if this is the drive, we'll call this one the drive, and this is the driven gear, then what we've got is a gearing up of 2:1. However, if this was the drive gear, if this was the one I was turning, I will find that this one will turn slower, and then I would say a gearing down of 2 to 1.
Were you not recording?